When we talk about a planet losing its atmosphere, it can sound abstract, like something distant, technical, almost cosmetic. But an atmosphere is not decoration. It is one of the most important systems a planet can have. An atmosphere controls how heat moves. It spreads energy from the side facing the star to the side facing away. It prevents extreme temperature swings. It slows down change. Without an atmosphere, a planet becomes unstable. Day becomes unbearably hot. Night becomes dangerously cold. And nothing exists to soften that contrast. On Earth, our atmosphere does far more than allow us to breathe. It traps just enough heat to keep the surface stable. It shields the planet from radiation. It protects the surface from the constant stream of particles coming from the sun. It acts as a buffer, a stabilizer, a regulator. Most stable planets depend on this balance. Lose the atmosphere, and the planet doesn't simply become different. It becomes hostile. This is why scientists pay so much attention to atmospheres when they study other worlds. It's not because atmospheres are rare. It's because they are fragile. They exist only when multiple conditions are met at the same time. Temperature must stay within a narrow range. Gravity must be strong enough to hold gases in place, and the planet must be protected from external forces that slowly strip those gases away. If any one of those factors changes, the atmosphere begins to fail. And that failure doesn't happen all at once. At first, the changes are subtle. Heat distribution becomes uneven. Weather patterns shift. The system loses efficiency. Over long periods of time, those small imbalances grow. The atmosphere thickens in some regions and thins in others. Circulation becomes unstable. Energy gets trapped where it shouldn't. This planet once had an atmosphere capable of regulating its climate. It had enough gravity to hold it, enough mass to sustain it, and conditions that, early on, may have looked surprisingly familiar. But the atmosphere it has today is nothing like what it once was. Something disrupted the balance, and once that balance was disturbed, the atmosphere stopped behaving as a stabilizing system and started behaving like a problem. Instead of distributing heat, it strapped Italiano. Instead of moderating temperature, it amplified extremes. Instead of protecting the surface, it accelerated change. This is the moment where a planet crosses an invisible line. Before that line, recovery is possible. After it, every feedback loop begins to push in the same direction. Heat leads to pressure. Pressure leads to chemical changes. Chemical changes alter how energy is absorbed and released. The atmosphere becomes heavier, denser, more hostile. And once that process begins, stopping it becomes extraordinarily difficult. This planet didn't lose its atmosphere overnight. It didn't vanish in a single catastrophic event. It collapsed gradually, step by step. The system that once kept the planet stable began working against it. To understand how that collapse happened, we have to look at what changed first. Because the loss of the atmosphere wasn't the cause, it was the consequence. The first thing that changed on this planet wasn't the atmosphere itself. It was how heat moved across the surface. Because of its slow and reversed rotation, sunlight no longer spread evenly. One side of the planet absorbed heat for far longer than it should have. The other remained in extended darkness. This imbalance mattered more than it seemed. On most planets, rotation helps smooth out temperature differences. Heat is redistributed. Energy moves. The system stays within limits. On TS planet, that mechanism failed. Heat began to build where it couldn't escape. Surface temperatures rose slowly at first, then faster. The atmosphere responded the only way it could. It expanded. As gases heated up, they became more energetic. They pushed outward. Pressure increased, and the structure of the atmosphere began to change. Instead of circulating efficiently, the air grew stagnant in some regions and turbulent in others. Weather patterns became extreme. Stability disappeared. This set off a feedback loop. Higher temperatures caused more heat to be trapped. More trapped heat increased atmospheric pressure. Higher pressure altered how sunlight was absorbed. The planet entered what scientists call a runaway greenhouse state. Once that process begins, stopping it is extremely difficult. The atmosphere grows thicker, not thinner. Cloud layers become dense and persistent. Heat that would normally radiate back into space becomes trapped. From the surface, the star never truly sets. The planet becomes locked in a cycle of constant overheating. As temperatures climbed, chemical reactions accelerated. Molecules broke apart. New compounds formed. The composition of the atmosphere shifted. Gases that once helped regulate temperature became part of the problem. They absorbed more energy, held on to it longer, and released it inefficiently. Over time, the surface conditions crossed another threshold. Liquids could no longer remain stable. Oceans, if they ever existed, would have evaporated. This is the critical point. Most planets never cross. Onsekro said the atmosphere stops being a protective layer and becomes an amplifier of destruction. The planet's climate didn't just change. It collapsed into a new state, and that new state made recovery nearly impossible. But the story doesn't end there, because even a runaway atmosphere can only persist if the planet is able to hold on to it. And this planet was about to face another problem, one that would slowly strip away what remained. Even a runaway atmosphere doesn't disappear on its own. For a planet to truly lose it, something else must be missing. Protection on Earth. Our atmosphere is constantly under attack. Charged particles stream outward from the sun at incredible speeds. Over time, those particles can strip gases away. But Earth has a defense. A magnetic field. That invisible shield deflects much of the solar wind, preventing it from directly interacting with the atmosphere. Without it, our atmosphere would slowly erode. This planet never had that protection. Its interior cooled early. The internal motion needed to generate a strong magnetic field weakened, and without that field, the planet was exposed. As the atmosphere expanded and heated, it became easier to strip away. The upper layers thinned, particles escaped into space. The process was slow, measured in millions of years, not days or centuries. But it was relentless. The solar wind didn't need to tear the atmosphere away all at once. It only needed to remove a little at a time. Over long periods, that loss accumulated. Lighter molecules escaped first. Hydrogen drifted away, water vapor broke apart, and its components followed. What remained grew heavier, denser, more hostile. The planet didn't just lose its atmosphere. It lost the parts of it that mattered most. And once those components were gone, recovery became impossible. A planet can rebuild its atmosphere only under very specific conditions. Volcanic activity must replenish gases, temperatures must remain within limits, and the planet must be able to hold on to what is released. This planet failed on all three. Its surface was too hot. Its gravity couldn't retain lighter gases, and without a magnetic shield, anything released was quickly stripped away. The atmosphere didn't vanish in a single moment. It faded, slowly, irreversibly. Today, what remains is a dense, crushing layer, a remnant of a system that once might have been far more balanced. This matters because nothing about this process is unique. The same physical laws apply everywhere. Rotation affects climate. Climate affects atmospheric stability. And without protection, atmospheres do not last. Scientists study this planet not because it is strange, but because it represents an extreme outcome of familiar processes. It shows how close a world can come to stability, and how easily it can cross the line. Earth is not on this path, but other worlds might be, especially planets that rotate slowly, or orbit close to their stars, or lack strong magnetic fields. This planet is a reminder that habitability is not permanent. It is a balance, and when that balance is lost, the consequences can define a world forever. But the loss of the atmosphere wasn't the final transformation. It locked the planet into another state, one defined by heat. In the next video, we'll look at why this planet became hotter than it ever should have, and what that tells us about how planets fail